This right here is a structural test laboratory. It's the longest structural reaction floor in the United States. This is a very, very strong floor to test structures on it. So you can build bridges here. You can build a bridge here that's 200 feet long, 3-lane wide, and put 50 years of traffic on it in about a couple of months.
This is Bob Duchesne's Wild Maine, a show about the outdoors. And we often deal with hunting, fishing, wildlife, and outdoor recreation. But we're often interested in our natural resources and what we're going to do with them to create jobs in the new economy. So this show can be very different from week to week. Next week, we'll be talking about whether eastern cougars are really extinct in Maine. And that couldn't be more different than today's show, where we're talking about all of our northern forest trees and what are we going to do with them. If you've given up wondering where all yesterday's jobs went and you're now wondering where all of tomorrow's jobs are going to come from, you'll be glad you tuned in this morning. We're heading inside the Advanced Structures and Composites Center at the University of Maine. We're going to make stuff. We're going to break stuff. And these are tomorrow's forest products jobs today. Bob Duchesne's Wild Maine is brought to you by Hammond Lumber, Napa Auto Parts, Doors Equipment, and EBS.
Habib Dagher. I'm the Executive Director of the Advanced Structures and Composites Center at the University of Maine, and I'm also a professor in the Civil Engineering Department.
We're in the lobby of the Advanced Structures and Composites Center with Habib Dagher. It's right next door to the Process Development Center in the University of Maine campus. We had a show from there a few weeks ago and discovered that if you take all those big fibers that our trees are made out of and break them down into tiny fibers, you can put them back together in extraordinary new ways. Here in this building, the Advanced Structures and Composite Center, you don't even have to break down the big fibers into little ones. You can take chunks of wood, flakes of wood, sawdust of wood, and depending on how you glue it back together, you can make 18-story buildings without steel and concrete. You can make buildings and even tents that can survive a bomb blast. And it's not just wood.
This center brings advanced materials into construction. We try to use as much wood as we can in terms of bringing wood in different ways to different applications in the construction business. What we do is we work with companies across the state of Maine, the country, and the world to help them develop new products that use new materials that will last longer, that will be less expensive, that could have a smaller environmental footprint. So we're experts in materials and structures. That's what the lab does. And the way we stay in business is we win contracts from companies across the country and the world to do research for them. We have over 500 clients from across the world that send their money to Maine for us to do research and development.
And pay local people.
And pay local people, right. So we're a technology business that happens to be located on the University of Maine campus.
There's a lot of new inventions we're starting to make right here in Maine, and we're about to take a look. We're going to step into a room that is the size of a football field. On one end, they make stuff. On the other, they try to break it. When you ask yourself, where are Maine's new jobs going to come from, look here first.
Absolutely. We live in a technology world. The biggest and most important race we need to win are this technology race and the education race. By having the best technology, that's how you spun off businesses. If you look at the iPhone, it's a technology. The iPhone is a technology. So we are doing the same thing. We are in a race, technology race, to develop new products that could be sold in the marketplace. We have a bridge technology that we developed called the bridge in a backpack. We'll get to see it in just a minute. It's a bridge that can inflate out of a bag. You can inflate a 60-foot long bridge out of a hockey bag, your main hockey bag, and then you can fill it full of concrete on site. You can bend these arches to any shape you want and fill them full of concrete on site. That spun off into a business. We have a number of patents on this. A private entrepreneur in Maine came here and saw this technology, raised millions of dollars, hired some of our students, and there's a business in Maine making these bridges right now. And just last week, a little over a week ago, they announced a partnership with one of the biggest construction companies in the world called Terre Armée, which is part of the Fressinet Group. 22,000 employees, 100 countries across the world. They've agreed to take this technology and help basically market it across the world, yet still we're going to be making it in Maine. But that's an example where ideas can come out of a lab like this and all of a sudden become a business, and that's what we try to do with a lot of the work in this lab.
We're about to enter the lab. I've been given a hard hat and goggles, and as we go into the lab, we are being watched.
And so this is a safety office. That's what you walk in first, and you really can't go into this lab without being watched and seen by the right people. And you can see everybody's watching and seen. It's a very big laboratory, 100,000 square feet, 180 people work here. We have 130 students. We've got to keep everybody safe. So that's one of the safety is our number one priority. We're entering the high bay area for the lab. The lab is U-shaped, and you can think of it as a place where you can design products, make those products, and test those products. And that's what makes this lab very unique. You got designers, you got builders, and you got testers. And then by having all these three functions under one roof, we're able to develop products very quickly for companies. So this part of the lab is where we actually, once we've designed a product, we go over to that end, we make the product, and we could go over here and test the product. So we're going to see how we can design, build, and test products here as we walk through the lab.
Okay.
Yeah. So right over there is the bridge and a backpack that I just talked to you about earlier.
We're in the lab looking left. In one corner of this room, a room the size of a football field, there's a demonstration area for this bridge and a backpack. And what we see is a tube. It's about 30 feet long, this one is anyway. They can be much longer. It's black. It's arched like a rainbow. It's about a foot in diameter, I'm just guessing, and it's flexible, maybe like a toy slinky, or more appropriately, it reminds me of some of the round plastic heating ductwork that I have in my basement. All of it. This whole span can be collapsed down into something the size of a backpack and carried easily by one person. Once put in place, the tube is inflated like a balloon, formed into the proper shape over a mold, and resin is applied to harden the tube into the exact shape you want.
So this is a model of the bridge. You can make these things, we've made them up to 90-foot spans in the lab. So this happens to be a smaller 30-foot span right here. And you have these arches that start in this hockey bag right there that can be inflated. They can be bent into any shape by pushing them against this mold. And then we infuse them with the resin. And within about 3 hours, the tube that you have a hollow tube that's twice the strength of steel.
Think about this. Everything here is really portable. One person can carry an arch. Two people can form it into place. Think of the places in Maine and in the world where building bridges with this technology lets you do things you couldn't do before. Cheaper and easier. You take a series of these arches and space them as you need them to support the bridge deck.
They're placed typically about 6 feet apart. These arches are placed 6 feet apart. Then on top of that, you put a composite decking system. You lax screw it into the empty tubes, and that stabilizes the arches. That becomes the decking. And then there's a hole on top of each arch, and a concrete truck pulls up, pump truck, and it pumps concrete into the arches and fill them up, just like a straw being filled with water. You fill it all up, and it takes about 3 hours to do that on a 2-lane bridge. And then when the concrete sets, 2 or 3 days later, you just backfill it with sand. And then you pave the bridge. We've been able to build highway bridges in less than 2 weeks.
Now, you're thinking this all sounds good in theory, but it's a long way from becoming a reality in the real world. Actually, it already is.
We have a bunch of bridges here across the state of Maine, as you see here. Number one, the first one we built was in Pittsfield, Maine, where we learned a lot on that. Then the second one we built was in Anson, North Anson, Maine. And that one was a 30-footer, 2-lane bridge. We got in there. There's a company out of Bangor who won the contract to build it. And then they removed the existing bridge, the concrete bridge out, put this new arches in, installed this bridge. The whole thing took less than 2 weeks.
Oh, my.
Yeah. That was in North Anson in 2009.
Wow.
And then since then, we've got over 21 bridges built right now. And then we're hoping now with this new agreement with Terre Armée, which is the new company they partnered with us to take this all over the country and the world.
There are bridges like this in Bradley, LaGrange, Ellsworth, Belfast, Edmonds, Caribou. They're now being built in other states across the country.
This technology could be 20 or 30% less expensive than existing on a first cost basis. But you got to have the right site. Like it's not a bridge for every site, right? You have to have a place where it makes sense to put an arch. It has to have good foundation conditions. So there's tens of thousands of bridges across the U.S. that actually are suitable for this kind of technology, but other places where you really shouldn't be using it.
These bridges are beyond being experimental. They've been tested and rated and approved for federal funding. They're expected to last even longer than traditional bridges because the concrete is sealed up inside these tubes. Concrete is strong, but it doesn't always weather well, so bridges might expect a lifespan of 50 to 80 years. These bridges are expected to last over 100.
I'm going to show you another technology we've developed with wood here that to make blast-resistant wood structures, so wood buildings that will withstand truck bombs and car bombs.
That's right. We're going to make stuff out of Maine wood that you can't blow up. That's next. Habib Dagher is Executive Director of the Advanced Structures and Composites Center at the University of Maine. If you're still with us after the break, we'll also show you how Maine technology is going to make landing on Mars possible. This is Bob Duchesne's Wild Maine on Sports Radio 92.9, The Ticket. It's Bob Duchesne's Wild Maine on Sports Radio 92.9, The Ticket. I'm with Habib Dagher, Executive Director of the Advanced Structures and Composites Center at the University of Maine. These are the guys who are inventing tomorrow's technology today, tomorrow's jobs today. And they're solving real-world problems. We're in a room that's the size of a football field. There are numerous projects going on in here. Some of the equipment I'm looking at is used to make stuff. Much of the equipment is used to break stuff. One thing this lab is particularly designed to do is to test how well new technology will age and weather and wear out. They can put years of stress on a part in just a relatively short period of time. And when necessary, they'll blow stuff up. One real-world problem Maine was asked to solve is this. In many troubled parts of the world, you need fast housing for lots of people. And this may be in places vulnerable to car bombs and mortar attacks. You can't make bunkers for everyone, too expensive and too time-consuming. You can't armor everything, same problem. Is there something you can make fast out of wood in such a way that you can't blow it up? Habib Dagher.
This is a piece of a building.
Yep.
It's a wood building, a stick-built wood building. The U.S. Army Corps of Engineers came to us, and you remember during the Kosovo war we had in Kosovo, they were going to put 4,000 people out in Kosovo, but the way you build, what you do to house people for 2 years, you usually build what we call stick-built wood homes. They take wood and they stick-build them out there. That's what the Corps of Engineers does, and they'll house thousands of our troops for a couple of years. You don't want to put them in tents for 2 years.
Right, yeah.
So what you do, but the problem they were concerned about is truck bombs and car bombs, and what happens to these wood structures. So we developed a coating for wood. You can see that's a 2x4 that's coated with a 1 millimeter thick coating, a very, very thin coating that you see here, and that makes the wood absorb 7 times more energy before it breaks.
Okay. 1 millimeter coating?
Yeah, yes, exactly.
And how is it?
And here's an example of how it works. Right over here, you see 2 pictures. These are 2 pictures of 2 wood buildings, identical buildings. One that's a standard building with no coating, that's the building with coating. We built these buildings, the panels right here at the university, and shipped them to Eglin Air Force Base. And then the Army, the U.S. Army, detonated truck bombs at the same distance between the 2 buildings. So the truck bombs between the 2 buildings, exactly at the same distance, detonated a truck bomb. And you see the building on the left is all destroyed, which is a normal wood building and no coating. The building with the coating was intact.
A millimeter
a millimeter coating. And
protected a building like this. So you can't even tell there was a blast.
That's correct. That's correct. And so this technology we have some patents on as well. But what I'm really excited about right now is the ability to be able to build hurricane-resistant homes and tornado-resistant homes in the hurricane belt zone. So we're working right now with the state of Mississippi, University of Mississippi, Mississippi State University, and in Florida, and the National Institute of Standards and Technology to take this technology into the hurricane zones and build buildings that will hopefully would be better resistant to hurricane loading. So we need to dial down this technology, but that's too strong for hurricanes in essence, because of the blast that it withstands. So we're looking at dialing it down and adapting it to be able to build wood buildings out of it. But think about the potential where we can have our sawmills in the state coat the wood before it goes, and then ship these coated wood members to the hurricane zones. So that's where we're heading with this technology.
That's what engineers are really good at the University of Maine, understanding why and how things break. If you put too much stress on a 2x4, it'll break, and it'll break at a knothole or weak spot in the grain. By putting a simple 1 millimeter of hardened coating on that wood, all the weak spots are sealed together and can't move. The same board is 7 times stronger. Yet you can still drill it, nail it, and screw it as if it were just like every other board. Well, if Maine can make a bomb-proof house, can we make a bomb-proof tent?
This is another technology that's graduated from the lab now. It's a business. There's 2 businesses in Maine producing that. And these are ballistic, this is the ballistic tent system. We call it the modular ballistic protection system. The Army came to us a few years ago and said, look, when we send troops to hot areas, hot zones, they have to move often, quickly every week. We move from one area to another, pick up a tent camp, move it somewhere else. When you do that, you don't have time to put sandbags around your tent camps or build barriers, physical barriers. So the concerns are truck bombs, car bombs, or mortar attacks on the tents. They asked us, can you help us develop ballistic tents? The Army tried to do this for years using Kevlar blankets, and that really didn't succeed. It was too clumsy, too difficult. Then what they try to do is they use ballistic panels mounted on a metallic tent frame. You see these panels right there, and they use big steel joints, connectors, to connect the ballistic panels to the steel tent frame. What happened is under blast load, when a bomb goes off or a mortar goes off, the mortar blast force would push on the ballistic panels, which in turn push on the tent frame, and the tent frame breaks up. The ballistic panels go flying across the tent. That didn't work very well.
Explosions are powerful, but brief. There's a tremendous amount of force, but it's over in a heartbeat. If you put rigid panels on rigid metal poles, attaching them with rigid hardware, the force breaks the fasteners and the panel goes flying into who is ever in the tent. But if you strap the panels on, using just ordinary straps, they give a little during that blast measured in milliseconds, but don't have time to fail before the blast is over. The panel stays put. These aren't even unusual straps. You can buy them locally and tie your canoe down with these.
And now we have this ability to build what we call a ballistic tent. So this tent now is able to protect troops that go inside of it. So and it takes only a few minutes to put up these ballistic panels on a tent, and you can take them with you on the road. That can pack in a small container. And so when you go inside, you're in the field, you go inside to go to sleep in your tent, you take your helmet off, ballistic helmet off, you take your ballistic vest off, and you're vulnerable. But in a tent like that, it's like you go to sleep inside a big helmet. So we've turned the tent into a large walk-in helmet. And so now this technology has been approved by the Army now. And we have 2 companies in Maine that are producing these ballistic panels, and they've been sold into Iraq and Afghanistan and other places as well. That's an example again of a technology graduating from the lab and going into the private sector.
I would think a private company couldn't make these fast enough right now. There must be a lot of demand.
There's a lot of demand, exactly, but that's an example of a technology that, again, what we try to do in our laboratory is develop technologies that will graduate and become businesses or part of businesses.
We'll take a break, and then we'll go to Mars. That's right. We're standing right next to a device made in Maine that will help us land on Mars. Habib Dagher is showing me around the Advanced Structures and Composites Center at the University of Maine. So we'll look at this, and then we'll try to break some more stuff. This is Bob Duchesne's Wild Maine on Sports Radio 92.9, The Ticket. This is Bob Duchesne's Wild Maine. Habib Dagher is Executive Director of the Advanced Structures and Composites Center at the University of Maine. They make stuff and they break stuff. And once they make it so that they can't break it, the stuff is ready to go to market and create Maine jobs. Some of this stuff is out of this world. We're standing next to a large brown donut. It's about 10 feet in diameter and it's suspended in the air. There's a bunch of pulleys and gadgets mounted on it that are designed to push and pull and twist this donut in every direction possible, trying to put on it all the stress it would undergo if you tried to punch it through the atmosphere on Mars. So here's the problem. When you put men on the moon, it's only about 1/6 the gravity of Earth, and there's no atmosphere to punch through and no friction with that atmosphere to heat up the lander. When we go to Mars, it is a smaller planet, about 38% the size of Earth, but that's twice the gravity of the moon, and it has an atmosphere. How can you slow down the lander in the early stages of entry? The answer is right here in Maine.
We're going to take spacecraft that will house people that are traveling at much faster than the speed of sound. That enter Mars's atmosphere, you got to slow it down. If you remember the Mars rover mission, when we put up, that was only about a 1 ton. The whole satellite that we sent out there, the spacecraft was 1 ton. We're talking about a 40-ton satellite right now. And that you can't just slow it down by pulling a parachute on it. So what we do is we inflate from the nose cone of the spacecraft. I'll show you right over here. We inflate these donuts, basically to form essentially this tori
sort of
structure.
It's like a heat shield, or what?
Yeah, the pink is a heat shield on top of it. And so this whole unit that you see here inflates from the nose cone of the spacecraft as it enters Mars's atmosphere. And when that whole thing inflates, it becomes like a big airbag, but essentially it works like a reverse airbag because it's very stiff enough that as the spacecraft enters the atmosphere, it slows it down. Okay, and so the goal here, our job here, is to help NASA design a structure that slows down the spacecraft so we can safely land people on Mars.
So this would slow it down initially as it enters the atmosphere, and then you go to parachutes later?
Exactly. Once it slows down enough, you pull a parachute on it. So you can see this testing we're doing right now is we're bending and twisting this tori structure in our laboratory to simulate the stresses it sees as it enters Mars's atmosphere. So when it enters Mars's atmosphere at these very high speeds, hypersonic speeds, it's going to vibrate, it's going to bend, it's going to twist. And you imagine that. So we're actually replicating how it bends and twists right here with this rig and making sure it's going to hold up.
So a lot of the creativity in this lab is figuring out how to break stuff. There are the pulleys and twisters we just saw. Over here, there's a water jet feeding a bladder that puts an explosive impact on wood. You can test various boards and wood composites to see what holds up best. Sometimes you just want to vibrate something so many times that it falls to pieces.
Well, yeah, the reason we break things here is because we have computer predictions of how much load they can carry. So if we say a girder can carry 100,000 pounds based on our computer predictions, and if it's a new girder, nobody's ever built anything like this before, we test it to make sure it works. And then if we know it works, then industry can start using it. Right over here, we're walking through a structural test laboratory that allows us to test structures under load. For example, you can build a bridge here and put 50 years of traffic on it in a couple of months. Or you can build a building, put an earthquake on it, and see how it holds up, or a hurricane. And
so this is where you beat the crap out of stuff.
Exactly. It's a place where we can see how strong materials are, and are they going to hold up in the environment where they're going to be. So.
We continue wandering through the structures lab, alternating between things they make and things they break. Much of it is made with Maine wood. Much of it is made with low-grade wood, the kind of wood we're anxiously trying to find markets for now that some of the older paper mills have shut down. Some products made with sawdust can hold back the ocean.
Here's another technology we have a patent on right here, and this is a retaining wall. It's a retaining wall to build on the waterfront. You see a lot of cities in the waterfront will put retaining walls to tie-back wall systems to, or you can do it to build it behind your house. You might build a retaining wall. So these are rather than using steel, which corrodes in about 15 to 20 years in the salt water or in the water. These things are made with sawdust and plastics. It's made with 50% sawdust by weight and 50% plastics, and it's extruded into this Z-shape sheet pile. And I'm going to show you how we can lift these. It's see how I can lift that?
Oh, look at that!
It's very easy to lift.
Yeah.
If this was steel, of course, you wouldn't be able to lift that at all.
No.
Yep. And this is 100% recyclable, and it's corrosion resistant. So 100 years from now, you can pull that out of the ground and then break it up into pellets and re-extrude it in a different shape or form. But half the weight of this sheet pile is wood. It's sawdust.
Yeah.
And the other half is plastic.
And it can hold back the ocean.
It can hold back the sand in the ocean.
Which is going to be good because the oceans are rising.
That's true.
We're going to have to hold back more ocean in the future. You're starting to get the idea. At the Advanced Structures and Composites Center, it's all about taking old materials, and we'll call them feedstock and glue, though I'm sure those aren't the right terms, and we'll stick it all together in new ways that have new properties. I suppose it's not terribly different than the ancient Romans did when they learned how to combine cement and volcanic ash and aggregate to make concrete. They even learned to add horsehair to tie it all together better. For us, we've been pretty accustomed to making stuff out of wood, steel, and concrete, but as we get better at epoxies and resins and stuff, we get better at putting composite materials together. For instance, I'm now holding a block of something that is about the size of a football, It's a bunch of something held together by a rigid outer coating, and it's so light, I could lift it with one baby finger.
This is another product to replace railroad ties. See how light that is?
Oh, for goodness sakes.
Yeah. So this has it's stronger than concrete. You can saw it with a normal saw blade. So think you want to use railroad ties to build a wall behind your house, or you have to use creosote ties, and you deal with the chemicals and the creosote. And this thing is a lot lighter. Yep. It's stronger, and it's corrosion resistant, and then it's 100% recyclable. And people like it because architecturally you can run wiring through it. If you have a retaining wall near your house, you can put lights on it and so forth, or communication cables, whatever you want to do. So we're looking for entrepreneurs to build the retaining walls in Maine, and then to build also this railroad tie. So if any of your listeners are entrepreneurs, we're happy to show them the technology.
Well, that's fun, but let's go back to creative ways of breaking stuff. In front of me is a shallow tank filled with a couple of inches of water. It's about the size of 2 or 3 ping pong tables laid end to end, a little bit wider maybe.
This is a water jet machining system. It'll cut into steel, into 4 to 5 inches of steel, using a water jet, high pressure water jet. And then you see this foam that's being cut over there. You can cut it on this machine as well. So it sprays water, and the water has garnet particles in it, abrasive particles that go up at very high pressure, and you can cut through, I said, 5 or 6 inches of steel.
Then around the corner into the next huge room, we encounter something that can break really big stuff.
This right here is a structural test laboratory. It's the longest structural reaction floor in the United States. This is a very, very strong floor to test structures on it. So you can build bridges here. You can build a bridge here that's 200 feet long, 3-lane wide, and put 50 years of traffic on it in about a couple of months. Okay. You can build buildings here and put earthquakes on them, or hurricanes, and so forth. So this floor is 4 feet thick of mass concrete, and it has anchor points on a 2-foot grid. You see these blue frames out there? They're bolted down to the floor onto these anchor points. It's called a reaction floor or strong floor.
And that's just the floor. There's also a reaction wall. You won't believe how big this is. You can bolt massive things to it and shake them for months to see if they break. You'll see that after a break. Spoiler alert, there's a big wind turbine blade already attached to it right now, and they've been beating the heck out of it for weeks trying to see if they can break it. This is Bob Duchesne's Wild Maine on Sports Radio 92.9, The Ticket. This is Bob Duchesne's Wild Maine on Sports Radio 92.9, The Ticket. And today, we're at the Advanced Structures and Composites Center at the University of Maine in Orono. Habib Dagher is Executive Director, and he's showing me all the cool things they can make, which is also a pretty good view of where Maine's future jobs will come from. In this lab, they can make and break things to see how new composite materials can work. Many of them are made out of good old-fashioned Maine wood. We're now standing on the largest reaction floor in the United States. 4 feet thick of concrete that you can bolt things to and shake them up to see if they break. Next to us, a reaction wall. You can bolt things to it and shake them up. There are dozens of bolts, and each one is over 6 feet long and weighs maybe 120 pounds each. There is a wind turbine blade currently attached to the wall. And for the last several weeks, they've been pounding it up and down, simulating years of wear and tear to see if they could break it. If they can't break it here, chances are it won't break in a tower either. Of course, they don't want to break the wall, so you can imagine how thick it is. The beep?
It goes underground 30 feet. It's all mass concrete, and it's pinned to ledge. So this is directly pinned to ledge. It's strong enough to be able to hold up the blade so the blade doesn't fall over. Okay? And the blade is bolted to the wall right now, and this blade is 160 feet long. It's hard to tell distance here. This is as long as as high as a 16-story building. Okay, that blade, but you can't tell here because, of course, the lab's so big you can't see that. You can't tell that. So that's as long as a 16-story building. And what we're doing now is we're putting it through the equivalent of 25 years of wear and tear in the real world. We just finished a series of tests right now, but I have a video to show you how actually it runs. But I want you to come and see how the blade is attached to the wall. So the blade is attached to the wall right here using a bunch of bolts. Yep. So it's bolted into the walls using an adapter plate. And we have holes in the wall to attach the blade to the wall.
I've arrived in a good day. They are just starting to unbolt the blade so they can lower it to the floor. Then they'll actually cut it open and look for any internal damage that 25 years of simulated stress may have caused. Nobody in the world is better at breaking stuff than the University of Maine. And once we know it's made well enough that we can't break it, we can put real structures to work. I'm standing beside that big test blade, looking at some big photos of other stuff, when Habib directs my attention to a screen below all that, showing a video of a wind turbine at sea. A turbine anchored to the ocean floor near Castine. And this turbine is being smashed around by storm waves.
What you see below that is the first offshore wind turbine in the United States. This was designed and built in this laboratory, and it was fabricated in components in this lab, shipped. It's made out of concrete, yet it floats. It's a floating wind turbine. And it was built right here, it put on 3 trucks that went to Brewer at Chimbro's facility in Brewer, and it was reassembled there and placed in the Penobscot River, towed down the Penobscot all the way to Castine. When it got to Castine, we had 3 mooring lines that connected it to the seafloor. We already had also an undersea cable that came from a CMP power line. We connected it up through the turbine, and then the turbine was putting electricity on the grid for a year and a half off Castine Harbor. This became the first time offshore wind energy got into the grid in the United States. But what's unique about this technology is the first wind turbine, floating wind turbine in the world made out of concrete with a composite tower on top of it. A very lightweight tower. But that's a 1:8 scale version of a 6 megawatt machine we're going to put off Monhegan Island here by 2019. Very exciting project. We just won a $40 million grant opportunity from the Department of Energy, and this will be the first floating wind farm in the United States off Monhegan Island. You can see Monhegan Island on the lower right-hand corner. These are the 2 full-size units. They'll have a rotor diameter of 500 feet, 550 feet roughly. And that's Monhegan Island. It'll be about 3 miles south of Monhegan Island where this test will take place.
So these are big. They're made out of concrete in a way that they float. Now, what about this storm I'm watching hit it?
This is a 50-year wave storm going over the unit. So this hull is being subjected to a 50. See how big the wave is relative to the hull? And in that environment, it moved off axis about 5.9 degrees. So you have a 50-year storm. It moved 5.9 degrees. Now, this is to prove that the technology actually works. We had over 60 sensors on this hull that monitored the motions of the hull, the stresses in the mooring lines, compared to what our computer predictions are, and they were right on. And because our computer predictions were so right on, the Department of Energy decided to invest in us that $40 million to move forward. What's very exciting is this will be the first offshore wind floating farm in the United States. What's exciting about Maine is that Maine, our biggest untapped renewable resource in the state of Maine, is offshore wind. Within 50 miles of the coast of Maine, we have 156 gigawatts of offshore wind. A gigawatt is roughly a nuclear power plant. So we have 156 nuclear power plants worth of wind just blowing off the coast of Maine. And our job is to bring that energy cost effectively so it can compete on the grid with no subsidies. That's our goal. And in the meantime, if we can actually build this technology and develop it in the state of Maine, we can put thousands of people to work building this infrastructure that will allow us to reduce our reliance on fossil fuels. At $4 a gallon in the state of Maine, at $4 a gallon, and that was not too long ago, and those numbers we're going to get back at $4 a gallon, $6 billion was leaving the state of Maine every year in fossil fuel prices. $6 billion. So what we see right here is a 150 scale version of a floating wind turbine of our 6 megawatt that we're going to put off Monhegan Island. So this is about 1/50th the size. And you can see right over there we have a human being standing on it, and you can see the size of that human being. So it has 3 flotation columns on the outside. Each one is 30 feet in diameter and about 120 feet high. So it has 3 flotation columns made out of concrete, like big concrete air cans. But these air cans are as big as a 12-story building each, and that's what we're talking about. And this unit is a 150 scale, and we test it in this environment. We test a lot of things at 150 scale. to see how they perform. So we can put a 50-year storm or 500-year storm on these units right over here. So this allows us to prove out our numerical models and develop next-generation technologies.
Okay, I've got two questions. Habib keeps saying these floating towers are made out of concrete. So how do they float?
What makes it float is that there's air inside the concrete.
Okay.
So if you took a barrel of steel, okay, it's all closed, and then throw it in the water, what happens?
It'll float.
But we know steel doesn't float.
Well, yeah,
how does that
but
float?
the air does. Okay.
But the air does. So
Yeah.
now instead of making the barrel out of steel, let's make it out of concrete.
Okay.
Okay. Now why are we making them out of concrete? Because concrete lasts so much better than steel in a saltwater environment.
Yes.
So we're looking at a 100-year life for this hull. It's corrosion resistant. Plus, concrete exists in Maine. We mine it in Maine, right in Thomaston. So we're talking to the folks in Thomaston to actually use their cement to produce these hulls.
I guess that was obvious. A battleship made out of steel floats because most of the volume in it is still air. But here's what I can't figure out. These are enormous towers with huge blades rocking back and forth in the 70-foot waves of a 500-year storm, yet it's only rocking about 5 to 7 degrees. Is there some kind of dampening built into this? Why doesn't it rock more?
This is an excellent question. Yes, what happens here is this unit right below the water, you see, has these 3 arms that look like a starfish. Okay, these arms are each 30 feet wide, okay, and 20 feet deep. Okay, each one of these arms are about 150 feet long. So this is a 150-foot long arm, 3 of them under the water. So if the whole unit has to move, it has to move through the water. So it moves a lot of water. So it has a lot of dampening going on with that system. So the other thing that's really important is you ask ourselves, how does this only move 7 degrees or 6 degrees in a 500-year storm?
Right.
What's the trick? The trick is the natural period of that unit as it moves in the water is over 25 seconds. It's designed that way. Because the period of the waves, the big waves in the Gulf of Maine, the 50 and 500-year waves are about 17 seconds, not more than that. So by designing a natural motion period of these units at 25 or 30 seconds, then the waves don't activate it anymore. Okay, so it's almost like you're pushing a kid on a swing, right?
Yeah.
The natural motion of the swing is usually about 1 to 2 seconds or 3 seconds, right? And then what you do is you wait for the kid to come to a top stop, then you push, right? So you push at the same period of the swing. Okay. Now, instead of the swing, we have a floating turbine. Instead of you pushing the kid, we have the waves pushing the turbine, right? So if you try to push the kid, okay, halfway on the way up, what happens?
You stop him.
You stop him, and that's exactly
and he cries.
And it cries, and that's exactly what we're doing with this floating turbine. What we're doing is we've designed it so that the waves pushes it halfway around. Okay, then it doesn't really.
So the waves are fighting themselves.
They're fighting themselves.
Yeah.
That's exactly how we designed the unit.
Very clever. Every time the tower begins to lean over in a storm, the next wave straightens it back up again. Habib Dagher is the director of the Advanced Structures and Composites Center here at the University of Maine. What we do with Maine's forest and Maine's ocean is the key to a lot of new jobs for Maine citizens. But I want to get back to breaking stuff. So coming up, we'll try to make stuff cold enough to break, and we'll visit a wave and wind pool designed to break stuff. When Bob Duchesne's Wild Maine continues on Sports Radio 92.9, The Ticket. Welcome back to Bob Duchesne's Wild Maine on Sports Radio 92.9, The Ticket. I am in the company of Habib Dagher, Executive Director of the Advanced Structures and Composites Center at the University of Maine. You should know that Maine's engineering program is world-class. Research being done there has the potential to create many of our new jobs in the future. First, we have to work the bugs out, and that means breaking stuff. So far in today's show, we've already witnessed attempts to break stuff under normal weather conditions. So how about abnormal?
What you see here in the left-hand corner, this is a large environmental chamber. This chamber changes the environment from minus 40 degrees C to 50 degrees C. All inside of it changes relative humidity to test how materials hold up and hold up under extreme environments. Very important part. So we can take materials in there and test them, bend them, and twist them as you change the environment, the temperature, to see how they hold up.
Some things get brittle when they get colder.
Yeah, exactly. Some materials become very glassy and brittle. Many of you who are in the chemistry class here know that materials get very brittle under cold temperatures. So we can test these kind of phenomena right here. Right beyond that, what you see in yellow is a saltwater corrosion basin. So you can put materials in there to figure out how it'll hold up in a saltwater environment. So we can walk over there.
Mm-hmm. Also, right here in the lab, there's another new product developed in the center. It's a big red box that looks like a railroad car without the wheels. Here's the problem. There are thousands of shipping containers that enter the U.S. harbors every year. How do you really know what's in each and every one of them? Only a few get scanned. Many were probably sitting around on docks waiting to get loaded onto a cargo ship, and not necessarily with much security in any of those foreign harbors. What if somebody broke into one of them and had bad stuff hidden there? Good question. What if there were technology built into shipping containers that would automatically recognize when it was being broken into and phone in its location and status so that the threat can be instantly recognized and addressed right there and then?
Typically, a shipping container is made out of steel. This is made out of composites. And we developed it for the Department of Homeland Security. Mm-hmm. We won a contract to develop smart shipping containers that will detect intrusions going into them through any of the 6 phases. And what's unique about this is only a fraction of containers that come into the United States are ever scanned. So we have 5 or 10% at most are actually scanned. So the concern is somebody bringing in biological agents or nuclear weapons or other weapons through these containers. And how do you actually detect that? So we developed this technology, and it's been so successful that we can track if anybody tries to get into this container anywhere in the world. We know where the container is, and we know when they're trying to get in. The container has a brain inside of it, essentially, a computer in it, that will communicate with us anywhere in the world through satellite communications or through cell phone communications or through Wi-Fi. Mm-hmm. So if somebody cuts a hole in this container, it's going to call us up and let us know. And what's so significant is a big need for security of shipments. Mm-hmm. So we're about to spin off a new business in the state of Maine called Global Secure Shipping Inc. Global Secure Shipping Inc. will start making these containers here in Maine here in about a year or so.
It's important to note that we're playing in the big leagues here. Maine wasn't the only contestant to win this contract. It was the best contestant.
There was over 120 proposals from some of the best top companies in the world that competed, and we won the contract.
Oh, wow.
We won an idea. That's how we win these contracts. Mm-hmm. So and today this technology is advanced enough. We have a number of patents.
This is the funny thing about the Advanced Structures and Composites Center. From the outside, it doesn't look any bigger than other campus buildings. Then you get inside, and it's cavernous. We started in one lab that is as big as a football field. Then we hit a room more than twice as big that tested wind turbine blades. And now...
So we're going to take you in here to our ocean engineering laboratory.
This football field-sized room contains a wave pool that has a rotatable wind machine blowing over it. It operates on a 50-to-1 scale, meaning that if you make a model of something that is 1/50th the real size, this lab will produce winds and waves that are the equivalent size. You can do towing tests, variable water depths, scaled wind and wave conditions. Basically, you can replicate some of the worst storms possible anywhere on Earth and see if you can break your model. It's inactive at the moment. They have been testing one of those wind turbine models recently, and it was the first indication that all the lab's computer modeling was accurate.
This is a new structural thermoplastics robotics manufacturing laboratory. Very unique lab that allows us to make composites orders of magnitude faster than we can make them today. At the very end, we have a big 3D printer that prints molds out of thermoplastics, very high temperature molds.
A 3D printer, a big one. Now, your inkjet printer puts down 2D, length and width, but not height. A 3D printer puts down layer on top of layer. If it's a liquid composite material, you can make a rather detailed computer-directed shape, perhaps a mold that you can use to shape something else.
And then we have large compression molding equipment to make composites over these molds. and we can stamp a composite, heat it up, and stamp it over the molds in seconds and form it to any shape. Think about making a piece of a car body.
Think about making anything. Right now, it takes a long time to make the mold for a boat hull. If you could shape it all in a big 3D printer, you're off to the races, faster and cheaper. Imagine what that technology could do for Maine boat building. Imagine what any of this technology could do for Maine jobs. Out here in Bob Duchesne's Wild Maine, we've got wood and we've got ocean. See if you can match that, Kansas. I tell you what, if I were just going to college today and wanted a job with a big paycheck and a nice future, I'd go into engineering. Or radio, that's where the big bucks are. My thanks to Habib Dagher for the excellent tour of the Advanced Structures and Composites Center and for a look into the future. Remember, this show and all previous shows are archived on the web at 929theticket.com. Otherwise, join me next Saturday morning at 9 or Sunday morning at 8. Bob Duchesne's Wild Maine is brought to you by Hammond Lumber, Napa Auto Parts, Doors Equipment, and EBS on Sports Radio 92.9 The Ticket.